Okay, Stokes' theorem. Let me first write the theorem, and then I'm going to tell you a nice, interesting story about it, about the history of this theorem. So the theorem says the following. Let S be a surface, let's say piecewise smooth surface in R3. And I'm going to add here orientable. We'll explain the words in a minute. Piecewise smooth surface in R3. With boundary gamma in the positive direction. Yeah, that should work. And let F equals PQR, this is our field, and we're going to assume it's C1, continuous partial derivatives of PQ and R, in a domain that contains S. So in a region in R3 containing S. And then the statement of the theorem, then, so this is the formula of Stokes' theorem, taking the line integral over gamma, which is the boundary of S, and S is a surface, so gamma is a closed curve, it's the boundary of the surface, of the field F dot dr. So this is a line integral for a vector field over the gamma, which is the boundary of S, equals the surface integral over S itself, and S is now not a closed surface, S is any surface, not of F, but rather of the rotor, the curl, dot ds. So this is Stokes' theorem, and this is what the curl was. We discussed it in the previous clip. Okay. So before we do any examples, I want to explain some words here, and then discuss some remarks, and then we'll do examples. So the first thing is, what is S? So you should think of S as a surface. Here is an example of a surface. Something maybe that looks like this. Okay, can you imagine this surface? Here the surface looks maybe like a graph of a function or something like that. Good? Okay, so the surface is a two-dimensional object, and it has a boundary. The boundary, the word boundary is a bit confusing because it's not exactly the meaning of boundary that we've been using so far. Points that every neighborhood has points from the surface and not from the surface, because the entire surface is a boundary in that sense, right? As a region in R3. So by the boundary, I mean this boundary of the surface. Okay, I'm not. So if this is the surface, the boundary is just the curve around it. Okay, and if this is the surface, the boundary is still this. Clear? Is it clear what the boundary is for a surface? Okay. Now a piecewise smooth surface means it has to be smooth or comprised of a finitely many smooth surfaces that are glued along their boundaries. Okay, so for example, this is a piecewise smooth. This is smooth, and this is piecewise smooth. Okay, clear? Now, orientable is a tricky word. what we want is the normal to point in a specific direction. So I don't know, do you know what the Möbius strip is? Have you encountered it? Can somebody lend me a piece of paper that you don't need? Möbius. It's an O with two dots above it. Möbius. It's not in English. Definitely not in Hebrew. Thanks. So I'll show you what a Möbius strip is. So I'm just taking a strip of paper here. Where am I? Ah, there I am. So I'm taking a piece of paper here. Here's a piece of paper. It obviously has two sides, right? There's this side and there's the bottom side. Do you agree? Okay. Now what I'm going to do, I can close it like this and make a closed strip, a ring out of it, right? And it still has two sides. Now it has the outer side and the inner side, right? Everybody can see that. But I can do this little trick, and this is not something like an Escher drawing. This is something you can actually do. I'm taking the two sides, and before closing it, I'm flipping one. And now I'm closing it. Okay? And you get something that's a twisted band. You can put it on your hand. Okay? And this is called the Möbius strip. You spell it like this, Möbius. I think. There are these two dots on the O. And the interesting thing about it is that it doesn't have an inside or an outside. Okay, if you trace your finger, suppose you're saying this is the outside, and you take your finger and try, I'm not cheating now, you can do this on your own, and I'm just walking my finger along it, and when I get here again, I'm on the other side. I'm on the inside. It has one side. Okay? At every region, it looks like a two-sided surface, but in fact, it only has one side. And there's a nice drawing of Escher, if you know who I'm talking about, where you see these little ants walking in a line around it, but the last one meets the first one again, because they're just continuous. Okay? So is it clear what the problem here is? There's no clear direction of the normal, because if you say the normal is pointing outwards, if you continuously continue the normal, when you get here again, it's going to be pointing inwards. Okay? So this surface is not orientable. Okay? It's a cool thing. Here's the Möbius strip. You can play with it a bit and pass it around. But the point is that in this course, all the surfaces are going to be orientable, and we're not going to be dealing at all with those very, very interesting things for mathematicians that are non-orientable. Okay, so that's what this word means. It's good surfaces in which we can prescribe a direction of the normal clearly and obviously, and everything is good. Okay, good? So that's this word here. And then it has a boundary gamma. So gamma is going to be, let's blue gamma here. So gamma is going to be this. This is gamma, and it continues here in the back. This is gamma for this surface. Okay, so that's gamma, and the surface itself is the entire thing. This is S, and that's gamma. And I left out some words here. Gamma is going to be closed, simple, closed, piecewise smooth, whatever. And gamma has to be positively oriented as well. Okay, so gamma is in the positive direction. So remember, a curve, I can give it a direction. And what do I want the direction to satisfy? So this word positive here means that with respect, gamma, with respect to the surface of which it's a boundary, has to satisfy, kind of like in Green's theorem, that when you walk along gamma, here I'm walking along gamma, and pointing my left hand is going to point in the direction of the surface. So this would be the correct orientation for gamma that I'm going to call positive direction in this case. Okay? So when I'm walking along gamma, see me walking along gamma? Okay? My left hand has to point in the direction of the surface when I'm walking forward, of course. Okay? Now that's a bit tricky because this surface is just embedded somewhere in three-dimensional space. I can walk along gamma with my head down, right? If I were to draw this in Australia, I would be walking with my head down, like they do in Australia, right? And then pointing my left hand to the surface, when my head is down, I would be walking in the other direction. Do you see that? Okay, confusing. So the more precise notion is, when you're walking forward, your left hand pointing in the direction of the surface and your head pointing in the direction of the normal. So if I choose the normal for this surface to be in this direction, and it's orientable, so it's going to be in this direction everywhere, this is the normal, it's not going to flip suddenly and go downwards, then when my head is in the direction of the normal, my left hand has to be pointing in the direction of the surface. That's the positive orientation. Clear? When it's flat, when it's two-dimensional, that's the version it takes in Green's theorem, and then it's much easier. Okay? You're just walking along a flat surface. Clear? Another way of doing it is the right-hand rule, whereas here you're the right-hand rule. So when you're walking along gamma and your finger is pointing in the direction of the normal, your thumb in the direction of the normal, you should be walking along gamma in the positive direction that your fingers are pointing. So that's going to give you the same thing. Okay, just don't forget that when you're doing it this way, you need to use your right hand, and when you're doing it this way, you need to use your left hand, and it's really fun proctoring exams where you have questions about Stokes and all the students are doing all kinds of, funny things. Anyway, finally, the important thing about the theorem, the actual formula says that whether you're integrating along the blue curve gamma, which is the boundary of the surface of the field, that's the same as a double integral, a surface integral on the entire surface on the inside, but not of the field, of some derivative of the field, in this case, the curl. Okay? Do you see the similarity to the theorems we have been discussing, like Green's theorem and Gauss's theorem and the Newton-Leibniz formula? Okay, so let's make some remarks. So the first remark. So remarks. 1. Similar to, or let's write it, note the similarity of the fundamental theorem of calculus, or its Newton-Leibniz formula form. If I take the integral on an interval AB, I want to write it like this rather than the integral from A to B. It's the same thing. Of the derivative of a function, f prime, and actually I want to write it on the other side. Let me rewrite it. The integral on the interval AB of the derivative f prime equals the antiderivative, which I'm going to call f now, calculated at b, calculated at b minus calculated at a. Do you recognize from this kind of weird writing that this is precisely the Newton-Leibniz formula? That's how we calculate integrals. We take a function, we find that it's antiderivative, we recognize it as a derivative of something, and calculate the antiderivative between the two endpoints of the interval. Do you see that? So this is Newton-Leibniz. Then we have Green's theorem, which said, take the line integral over gamma, which was the boundary of a two-dimensional domain D, add a snake, double integral, move from the boundary of the domain, B and A, to the domain itself, D. See the similarity? and then take a derivative of what you have here. In this case, it was qx minus py, dx dy. So this was Green's theorem. Then we had Gauss. Gauss said, take a double integral, a surface integral, over S, which is the boundary of a domain V, now in R3. So S is now a closed surface of the field. Bless you. So S is the surface of a three-dimensional body, a three-dimensional region in R3V. This equals, add a snake, triple integral, move from the boundary to the region itself, V, but replace the field with some derivative of the field. In this case, it was the divergence. Oops. The divergence of F. This was Gauss. Do you see the similarity? And then finally, Stokes said, take the line integral over gamma, which is now, I don't want to use this notation because it's boundary in a slightly different sense of the field. And this equals, instead of gamma, the boundary, take the entire region, the surface. So you get a surface integral of, you added a snake, but you're paying a price and taking some derivative of the field, in this case, the rotor. So this is Stokes. So this is the full picture of the theorems that we're going to see in this course. It's not something you can use in solving exercises, the similarity between these four. It's just, I think it's important to see that these are not just sporadic kind of observations that wise people have made regarding these various integrals. In fact, this is one theorem. Okay, there's a general theorem called Stokes' theorem in differential geometry, of which all of these are special cases. Okay, they're in fact all forms of the same more general theorem. Okay, so what I want to show you is how to actually, something that's easy to see is that in fact Green's theorem, it's easy to see that Green's theorem is a particular case of Stokes' theorem. Let's do that. Okay, so this was remark number one. Remark number two, Stokes generalizes Green. So what do we mean when we say that one theorem is a generalization of another theorem? We mean that if we know Stokes, then we can retrieve Green's theorem by restricting somehow the data. Okay, so let's look back at Stokes' theorem. Stokes' theorem said, okay, your surface is a surface in three-dimensional space. You're taking the boundary, this is what you get. Okay? Let's assume, in order to discuss to discuss the appropriate framework for Green, let's assume that the surface is flat. It's in two-dimensional space. Okay? So if the surface is flat, if S is flat, the boundary is now going to be same thing. The boundary is going to be the boundary in the xy plane. Okay? And now when we calculate this, we're taking the, remember, what is a surface integral? It's calculating the field dot the normal, right? And the normal is only going to have an xy, a z component, right? Because if the surface is flat, if the surface is in two-dimensional space, what's the normal going to be to the surface? It's going to be 0, 0, 1. Do you agree? So the only thing that's going to survive from this is the z component. Is everybody with me? When we're calculating a surface integral, what we're calculating, so let's write it. in general, a surface integral of a field f dot ds equals, remember, we're taking the domain of the parameters du, dv, right? And we're calculating f dot the normal. Remember this? This is how we do a surface integral. Okay? Everybody with me? So if in Stokes' theorem, S is a surface in the xy plane, a flat surface, then the normal is just 0, 0, 1. Right? That's the normal to a surface in the plane. Does everybody see that? So when we calculate this, the only thing that's going to survive is the z component of what's written here. Do you agree? The p and the q components are going to meet zeros in this dot product and are going to vanish. Everybody with me? Okay. Therefore, we get, what do we get? The line integral over the boundary gamma of f dot dr, and now it's an integral of a gamma in the plane, because the surface was in the plane, equals, and now we get, by Stokes, let's again look at Stokes, what do we get? We get a surface integral of the rotor, the curl, dot ds. So the rotor times the normal, right? Calculate this, you have to take the field, in this case the field is the rotor, dot the normal. Does everybody agree? So the only thing that's going to survive is the z component of the curl. Good? What's the z component of the curl? Here's the curl. The z component is what we get it in K. It's q with respect to x minus p with respect to y. See that? That's the z component of the curl. So what we're going to get here is precisely the double integral over the domain of which gamma is a boundary. Now let's call it d. You can call it s, doesn't matter. Of qx minus py. You can call it S if you want to be consistent with the notation. This is precisely green. Clear? So qx minus py, this is the k component of the curl. Clear? Is this remark clear? So green is indeed a particular case of Stokes. Good? Okay. A story. I promised you a little story. So this theorem, Stokes' theorem, how do theorems get their names? So usually they get their name by the person that discovered the theorem, and therefore history attributes the theorem to him. Sometimes there are more interesting stories, like people buying theorems and calling them in their name, or people stealing theorems from their students, for example. And one of these interesting stories is the story of L'Hopital's theorem. You can read about it in others. In this case, the story is also interesting. So this theorem kind of showed up, according to what we know, in a correspondence, in a mail correspondence, not email. This is 19th century, mail correspondence between Stokes and another mathematician or physicist called Lord Kelvin. Maybe you've heard of him in physics. And this is around the year 1850. So Lord Kelvin wrote to Stokes. Stokes was a professor in Cambridge, in England, and wrote to him about this. The notation then was slightly different, and it was presented a bit differently, but it was basically this theorem, and Stokes found it interesting and decided to give it as a question to his students. And not just his students, there was a competition at the time called the Smith Prize. It was a very prestigious competition in Cambridge. And in 1854, in that Smith Prize competition, only the brightest students could it was a test, and one of the questions was, prove this theorem. And Stokes just gave it to the students. And I mean, we're not going to see the details of the proof because we're not doing many of these more sophisticated proofs, but it's not very, very deep if you know well how to write things, the notation, and things compile nicely like they do today, then it's not a very hard theorem. But many times theorems are more challenging when you don't have the right notation and the right way to say the words, and that was not the situation back then. The words have developed. The ability to say these things simply has developed greatly since then. So in any way, this was it was a question in that 1854 Smith Prize competition in Cambridge, and we don't know if any of the students actually solved this question. What we do know is that the winner of that competition in 1854 was another famous person you may have heard of, Maxwell, from the Maxwell equations in physics. And anyway, the theorem went down in history as Stokes' theorem, sometimes called the Kelvin-Stokes theorem. And this is the Kelvin-Stokes theorem is this version, this Calc 2 version of the theorem. The more general one is called Stokes' theorem. So that's the story of Stokes' theorem. What we still didn't do is examples. So I want to see how we actually use the theorem. That's going to be in the next clip.